laws of motion. Learning about second law of motion. Second law of motion. When two bodies, a heavy one and a light one, are acted upon by the same force for the same time, the light body attains higher velocity or higher speed than the heavy one. But the momentum gained by both the bodies is the same. The link between force and momentum is expressed in Newton's second law of motion. According to Newton's second law of motion, the rate of change of momentum of a body is directly proportional to the applied force and takes place in the direction in which the force acts. The rate of change of momentum of a body can be obtained by dividing the change in momentum by the time taken for change. So, Newton's second law of motion can be expressed as. Let us recount some observation from our everyday life. During the game of table tennis, if the ball hits a player, it does not hurt him. On the other hand, when a fast-moving cricket ball hits a spectator, it may hurt him. A truck at rest does not require any attention when parked along a roadside, but a moving truck, even at the speed as low as 5 ms raised to the power -1, may kill a person standing in its path. These observations suggest that the impact produced by the objects depend on their mass and velocity. Similarly, if an object is to be accelerated, we know that a greater force is required to give a greater velocity. One such property, called momentum, was introduced by Newton. The momentum, P, of an object is defined as the product of its mass, m, and velocity, v. That is, P is equal to mv. Momentum has both direction and magnitude. Its direction is the same as that of velocity, v. The SI unit of momentum is kilogram meter per second, kgms raised to the power -1. Since the application of an unbalanced force brings a change in the velocity of an object, it is therefore clear that a force also produces a change of momentum. Mathematical formulation of second law of motion. Suppose an object of mass m is moving along a straight line with an initial velocity u. It is uniformly accelerated to velocity v in time t by the application of a constant force F throughout the time t. The initial and final momentum of the object will be P1 is equal to mu and P2 is equal to mv respectively. The change in momentum directly proportional P2 minus P1, directly proportional mv minus mu, directly proportional m multiplied by v minus u. The rate of change of momentum is directly proportional to m multiplied by v minus u divided by t, or the applied force F is directly proportional to m multiplied by v minus u divided by t. F is equal to km multiplied by v minus u divided by t. That is equal to kma. Here, A is equal to bracket v minus u divided by t is the acceleration which is the rate of change of velocity. The quantity k is a constant of proportionality. The SI units of mass and acceleration are kg and ms raised to the power minus 2 respectively. The unit of force is so chosen that the value of the constant k becomes 1. For this, 1 unit of force is defined as the amount that produces an acceleration of 1 ms to the power minus 2 in an object of 1 kg mass. That is, 1 unit of force is equal to k multiplied by 1 kg multiplied by 1 ms to the power minus 2. Thus, the value of k becomes 1 from the equation F is equal to ma. The unit of force is kg ms to the power minus 2 or Newton, which has the symbol N. The second law of motion gives us a method to measure the force acting on an object as a product of its mass and acceleration. The first law of motion can be mathematically stated from the mathematical expression for the second law of motion. F is equal to ma, or F is equal to m bracket v minus u divided by t, or Ft is equal to mv minus mu. When f is equal to 0, v is equal to u for whatever time t is taken. This means that the object will continue moving with uniform velocity u throughout the time t. If u is 0, then v will also be 0. That is, the object will remain at rest. Example: a constant force acts on an object of mass 5 kg for a duration of 2 seconds. It increases the object's velocity from 3 ms to the power minus 1 to 7 ms to the power minus 1. Find the magnitude of the applied force. Now, if the force was applied for a duration of 5 seconds, what would be the final velocity of the object? Solution: we have been given that u is equal to 3 ms to the power minus 1 and v is equal to 7 ms to the power minus 1. T is equal to 2 seconds and m is equal to 5 kg. F is equal to m bracket v minus u divided by t. Substitution of values in this relation gives F is equal to 5 kg bracket 7 ms to the power minus 1 minus 3 ms to the power minus 1 divided by 2 seconds. That is equal to 10 Newton. If this force is applied for a duration of 5 seconds, bracket t is equal to 5 seconds, then the final velocity can be calculated by rewriting the equation as v is equal to u plus ft divided by m. On substituting the values of u, f, m and t, we get the final velocity v is equal to 13 ms to the power minus 1. On substituting the values of u, f, m and t, we get the final velocity v is equal to 13 ms to the power minus 1. Summary. Second law of motion. The rate of change of momentum of an object is proportional to the applied unbalanced force in the direction of the force. The SI unit of force is kg ms to the power minus 2. This is also known as Newton and represented by the symbol N. A force of 1 Newton produces an acceleration of 1 ms to the power minus 2 on an object of mass 1 kg. The momentum of an object is the product of its mass and velocity and has the same direction as that of the velocity. Its SI unit is kg ms to the power minus 1. That is all in this topic, students. Let us learn about Newton's third law of motion in our next topic. Learning is fun, isn't it?